Good morning, everyone. Welcome to our weekly lecture. I think there's something wrong with my computer. I'm trying to use, let me see if I can use the microphone. Let me, if I can use the microphone, hold on. Yesterday I had similar problem. There was an echo. Is there an echo now? Can you hear me? Please, somebody respond on the chat. No more echo, right? Thank you. I guess this is what I'm going to use. Yesterday, I had a problem. So today, we are going to continue with our discussion on chapter 4. We have so far looked at two or three types of reaction. These are the type of reaction you should know: decomposition. Should know what it is. Combination. We talked about combustion. And in section 4.3, we're looking at neutralization, acid base neutralization. We'll talk about the oxidation later on. These are the type of reaction. And so far, we have defined what an acid is. You should know what an acid is. You should know what a base is. We discussed this last time. All right. And we gave examples of acids, examples of base. Please, if you look at the left side of the screen on the PowerPoint slide, I do have examples of strong acid and strong bases. Strong acid and strong bases. You are expected to know the names and the formulas of the strong acid and strong bases. Down the line, as I mentioned last week, or if you are required to take CHM2, it will reach a point where they will require you, or you'll be required to know the names and the formulas of strong acid, strong bases. And we talked about the strong electrolytes, weak electrolyte last week. And even though we say ionic compounds are strong electrolytes, strong bases and strong acid are also considered as a strong electrolyte. They dissociate in H2O to produce hydroxide ion. For a base, it produces hydroxide ion, and for an acid, it produces, or they produce hydrogen ion. This one, when it is produced, it doesn't stay alone in H2O. You may see this, or you may have seen this polyatomic ion called hydronium. Is because water being with a partially negative terminal oxygen, they will the hydrogen ion will get attached or associated to oxygen atom in water molecules. Therefore, it will exist as hydronium. So hydronium or hydrogen ion, they are interchangeably used when defining a strong acid, strong base. Last time, we saw how to write the molecular equation, the total ionic equation, and the net ionic equation. We talked about the spectator ions, all right? And what are the spectator ions? Remember, you get to look at the physical state. I would like to use one example to pick up from those three types of equation. Let me just show you what we talked about last time: the net ionic equation, molecular equation, and the net ionic equation. Net ionic equation. This is what I'm trying to pick up from in terms of net ionic equation. So how do I know that? It's by using the solubility chart. All right, solubility chart. As I said last time, you will use this in the next quiz. So when I send out or when I post the quiz, you should have this to write the net ionic equation, total ionic equation, and uh, molecular equation. For acid-base neutralization, you also write the net ionic equation. For example, sodium hydroxide aqueous plus HCl aqueous, it form, all right, it form salt anionic compound aqueous plus H2O liquid. I've seen problems or question asking you to write the net ionic equation for acid-base neutralization. Acid-base neutralization. Remember, you split the aqueous phase in the molecular equation. What I do have here is the molecular equation. Molecular equation. You're gonna split this. It's gonna split this. You will split this. You don't split liquid. Since the mole ratio is 1 to 1 to 1 to 1, complete ionic equation will give us Na plus aqueous plus OH negative, you generate ions, plus hydrogen ion, this is aqueous, plus chloride ion, and then you equate to sodium ions plus chloride ion plus H2O. This is liquid. You don't split the liquid phase, the gaseous phase, and the solid phase in the molecular equation. So what appears exactly the same on either side, we call these spectator ions. These are spectator ions. They look alike on either side, and we cancel out. We cancel out that, and this will go. This will go. And if you look at net ionic equation for acid-base neutralization here, in the example I just gave you, it will be hydrogen ion, this is aqueous, plus hydroxide ion, this is aqueous, to produce H2O, to produce, mean to say this is H2O, which is liquid. This is the net ionic equation, net ionic equation. And you will see this in acid-base neutralization, acid-base neutralization. I want you to remember that also you'll be asked a question along those lines for acid-base neutralization. So let's look at the neutralization. And in neutralization, an acid reacts with a base to produce water and a salt. In net ionic equation, complete ionic equation, you will do the same thing. That's the way we did for H2O. You can do for any other acid. You can do for any other base. Remember, you need to balance the molecular equation first. Okay, so H2O will not be split. You don't split H2O in complete ionic equation. When you cancel out the spectator ions, you end up with liquid H2O as the product, as the product. That is acid-base neutralization. There are some neutralization reaction that produces gas. We call those gas forming reactions. And as far as the text is concerned, there are two types of reaction: those which produce hydrogen sulfide and those which produce CO2. When carbonate or bicarbonate react with an acid, what are those? These are compounds with polyatomic ion carbonate. This is called carbonate. And bicarbonate, this is carbonate. They produce carbon dioxide. This is the gas being referred to here. So when an acid react with any of the compound containing these polyatomic ions, they produce CO2 and H2O. If I don't know what the chemical formula for carbonate and bicarbonate, then there is no way you can relate to neutralization reaction that produce CO2. So first, if I know the formula for for an acid, and the chemical formula for carbonate or bicarbonate, and then I expect to see carbon dioxide as one of the product and water as one of the product. Okay, so here is calcium carbonate, and here is HCl. Okay, assuming that I don't know the products right here, I expect to relate this to this neutralization reaction which produce CO2, and carbonate produce CO2 and H2O. H2O. Okay. If you look at the physical state of if you look at the physical state of the molecular equation, you can tell which one you're going to split. I'm gonna split this. I'm gonna split this. I don't split this. I don't split this. That's where we are going with the net ionic equation. I've also seen that before, that you are asked to find the net ionic equation for an acid base. Neutralization involving those reactions that produce gas or gas forming reaction. This is bicarbonate, sodium hydrogen carbonate, reacting with hydrogen bromide. This is an acid, and the product gives liquid H2O and CO2. These are two classic examples on gas forming neutralization reaction. Gas forming neutralization reaction. You don't need to memorize the chemical formulas for the product on this side. Go back to the polyatomic ion table and look at the, for example, the second reagent or second reaction. It has sodium ion and a hydrogen carbonate. That's the ions for the formula. And what? Second reagent is hydrogen bromide, and these are the ions. If you look at the charges, on the ions and polyatomic ions, it helps me in writing the correct formula of the product. This is the crossover rule. Crossover rule. All right. Even though you see this NAPR, that is okay right here, but you are wondering why not this CH2O3. For this hydrogen and this hydrogen, we have two things. This will decompose into H2O plus CO2. This is gas and this is liquid. So this will decompose into these two products when you use this approach to write the chemical formulas of your product. I can also show you the first one. This has carbonate ion, which is -2, and HCl has chloride and hydrogen ion. If we do the crossover rule to write the correct formulas of the product, this is what we have. CaCl2. And you're gonna use the solubility chart here to predict which one is solid, which one is aqueous. Look at the calcium and chloride, it is aqueous. So I know this is aqueous. You can remember that, use the solubility chart. And of course, this, as I say, produce this, but it will decompose to produce H2O and CO2. This is gas. So acid-base neutralization that produce CO2 and liquid H2O. Please look at the chemical formulas of your reagents. Use this illustration to predict your what? Your product, and then you balance the equation. You balance the equation. After writing the correct formula, the next thing is balancing the equation. Then from balancing the equation, if you are asked to write the net ionic equation, that's what you will do. All right. I hear some background noise. Let me just cancel that. All right. I think that's good. So remember that. Any question on gas forming reaction that produce CO2? That's one of the gas forming. The other one is reactions that produce hydrogen sulfide. This is called, I know you may say this is the hydrogen sulfide, but the common name is just hydrogen sulfide. Hydrogen sulfide. Sodium sulfide with sulfuric acid produces sodium sulfate and hydrogen sulfide gas. Hydrogen sulfide gas is what is produced hydrogen sulfide gas. Okay. And what happening here is just a crossover rule again, using periodic table and polyatomic ion. You can predict the product on this side. Okay, you can predict the product on this side. Are these like double? Yes, Jennifer, double replacement reaction. It's the same thing. Metathesis reaction. Exactly. You can look at it that way. We cannot talk about in detail. When we say double replacement, it is all double replacement. But when we say acid-base neutralize, it is a specific type of double replacement reaction. Thank you. That is an example of that. But we are now focusing on, what type of gases are produced. And one of them is CO2, and the other one is hydrogen sulfide. It cannot be any other gas. Okay, so when you read on page 134, understand that what gases are produced when an acid react with a base to produce. Here are examples of, reagents, bases which produce CO2. We are all familiar with all these antacid. Okay, when you have indigestion, people do take this antacid, and the purpose of this is to produce or neutralize an acid. You look all of them, they do have what? They have hydroxide. And the hydroxide will neutralize the acid or react with the hydrogen ion in the acid. You can read more on the purpose of each one of them if you want to, how they work. But the purpose is to neutralize the hydrogen ions. Okay. Let's move on to 4.4. Special type of reaction we call redox. Sometimes we call this redox reaction. There are two types of reaction taking place here. You'll see over and over redox, redox, redox. What does redox? Two reactions. There is reduction and there is oxidation reaction. Oxidation reaction. Oxidation reaction is a reaction where there is gain of what? This is a loss of electrons, and this is gain of what? Gain of elect electron electrons. Electron or electrons. It can be more than one, or it can be 2, 3, or 4. So redox reaction are two types of reaction going on: gain of electron and loss of electron. When one species is losing, the other one is gaining. The electron is not lost, or electrons are not lost into the atmosphere. One species is losing, the other one is gaining. So two reactions taking place simultaneously, all right? And we just abbreviate it as redox reaction. So when you see oxidation, reduction, reaction, these are the two types of reactions. If you want to commit to your memory how you define that, they say oil rig, all right, oil rig. You can remember that, so that you say that oxidation is loss of electrons. That's how I can remember. What is oxidation? Oil rig. And then here is reduction. Reduction is gain of electron. You need to be able to differentiate those two type of reaction. Okay, there is oxidation, there is reduction. Two terms. Now, previously we looked at to classify a reaction as acid-base when H2O is produced. Gas form, there is a gas being produced. How do we know that this is a redox reaction? By keeping track of what? Electron. And remember, electrons are negatively charged. If sodium lose one electron to chlorine, all right, the arrow indicates the movement of electron. This will form cation. This will form an ion negatively charged. Positive and negative to attract. So we end up with this. All right. That's how redox reaction take place. Here is an example of redox. On the PowerPoint slide, there is calcium and oxygen reacting. A metal loses its one or more electron to a non-metal in the formation of ionic compound. Now, if sodium is losing, in this example, chlorine is gaining. There are terms used for dividing those two types of element in redox. Look at the PowerPoint slide. There is oxidized and there is reduced. I've defined oxidation, you know what it is. I've defined reduction, you know what it is. Okay. How do I identify reduce and oxidize? I normally use traveling agent. Traveling agent does not travel, but make people to do what? To travel. Every time I want to go somewhere, maybe I'm shopping for air ticket, I can use a traveling agent. A traveling agent look for the ticket, all right? So in a similar way, if you know oxidation is loss of electron, oxidation is loss of electron. What is oxidizing age? There is I wanted to say here, oxidizing agent, and then there is reduce agent. There is oxidizing and there is what? There is reducing agent. Oxidizing agent causes oxidation or receive electron, and this one donate electrons or electron, can be one or can be more than that. Oxidizing agent, reducing agent. In this example, this is oxidizing agent, and this is reducing agent. All right. Reducing is the one adding electron. Oxidizing is the one receiving. If oxidation is loss of electron, if oxidation is loss of electron, which one is causing the loss of electron? It's the oxidizing agent. This one is causing sodium to what? To lose electron, is oxidizing agent. If reduction is addition or gain of electron, this one is making chlorine to gain an electron. In this example, we say it's a reducing agent. And then to understand the oxidized, what is oxidized and what is reduced, reducing agent is oxidized. This is said to be what? This is oxidized. And reducing agent is reduced. Oxidizing agent, reducing agent, what is reduced and what is oxidized. Okay. There are 6 terms across the nation that students find so hard to really configure in their minds, and it's not only UNF, even at Harvard, MIT, this concept of oxidation reduction is not something you just read one time and you get it, unless you are you're a genius. All right. So 6 terms: oxidation, reduction, reducing agent, oxidizing agent. What is reduced and what is oxidized in the redox reaction? Those are the key terminologies. You should understand what they mean, and you should be able to recognize in a redox reaction. Okay. Let's look at this equation on the PowerPoint slide right here. Calcium solid reacting with oxygen gas to form calcium oxide. Calcium oxide. Metal will lose what? We lose electron, whereas non-metal gain. From the chemical formula, you know the ionic charge for calcium is positive 2. Oxygen is what? Negative 2, using the periodic table. So that when I write the correct formula, this will be calcium oxide. And of course, you balance out the equation because it was oxygen gas here, oxygen gas here. The point is, metal loses their valence electron. We're going to talk about that, but just understand that metal will always lose electron. And you see that the arrow or the electrons are going to oxygen in this case. If you can, use this analogy, use the periodic table and predict the ionic charges in the compound. And that will tell you where the electrons are coming and where the electron ended. So if I look at this, you don't have to memorize that calcium is positive 2 and oxygen is negative 2. Using the periodic table, predict the ionic charges from the formula. And then from here, what is oxidized and what is reduced, it has to do with what is going on the reactant side. It has nothing to do with the product side. All has to do with on the reactant side. So this is losing the electron, this is gaining electron. And remember, the one causing loss of electron is the oxidizing agent, and it is reduced. Oxidizing agent, all right? Oxidizing agent A is reduced. This is right here, reducing agent, and it is oxidized, all right? This is oxidizing agent, and is reduced. It's the opposite. I don't know, that's how it is. You use reducing and then oxidize. Oxidizing, it is reduced. So, right here, calcium is oxidized and it is reducing agent. It's donating electron. If reduction is addition of electron, the one adding electron is the reducing agent. Just the way I told you about the traveling agent, they make people do travel. Oxidizing agent make the other species to do what? To lose electron, and it is reduced because reduction is addition, it's being reduced. It is being made to lose electron. We say oxidized, oxidized. Any question on those 6 terminologies before I move forward? That's what I want you to, if I were you, I'll just go back again and write my own notes, what oxidizing agent is, what reducing agent is, and what is oxidized. Can you repeat oxidize and reduce? Yes. If you know what oxidation is, what reduction is, you will use those terms to understand what is oxidized and what is reduced. Oxidizing agent make the other species to do what? To lose the electron. For example, here, oxidizing agent, oxygen is making calcium to lose electron. How do we know that it has made calcium to lose electron? It is negatively charged. It has gained electron. It has made the other one to lose. So we say oxidizing, it's making the other one to lose, and it is reduced. To reduce is to add electrons, so it is reduced. So look here, reduced and the electrons here being gained. That's how I look at what is reduced. To reduce is to add electron. I'm adding electron to oxygen. I'm reducing oxygen, so it is reduced. Now, oxidize, if oxidation is loss of electron, oxidation loss of electron, what is oxidized is made to lose electron. It has lost electron at the end of the reaction. At the end of the reaction, the species has lost electron and it is positively charged. So if I know after the reaction, the species is positively charged or less in number of electrons, it is oxidized. It is made to, it has lost electron, in other words. I hope that makes sense, Anthony. Is that clear? Oxidize and reduce. Yes, exactly. That's how you look at it. And that is where we are going with that. We're going to talk about the oxidation numbers, which will be, handy in identifying what is reduced, what is oxidized. I'm defining this. I define oxidation, loss of electron, right? So it's not a big deal. You know what oxidation is, you know what reduction is, gain of electron, the reaction can taking place. They cannot occur singly, like, they do take place concurrently. You say redox for reduction. So here is reduction and here is oxidation. We say redox reaction, 2 types of reaction. Oxidation numbers or oxidation state are just charges, from the previous section. You are able to use the what? Polyatomic ion and the periodic table to predict the ionic charges. So ionic charges in some way are oxidation numbers. We use oxidation numbers to determine whether a species has gained or lost electron. Here is positive 2, this oxidation number, this oxidation number, and there are some rules for assigning oxidation number. Sometimes we use oxidation state, all right? Oxidation state or the ionic charges are used to determine if an redox reaction has taken place. We assign oxidation numbers to each element in a neutral compound. What do we mean by neutral compound? This is a neutral good. This is a neutral compound. All right. This is a neutral compound. This is not a neutral compound because it has an overall charge. All right. This is an element. It's neutral. This is a compound. It's neutral. They have no overall charge. They have no overall charge. So in redox reaction, we keep track of number of electron loss or gain by assigning oxidation numbers. And here are the rules you need to remember and you need to commit to your memory. Atoms in their elemental state have an oxidation number of 0. What are elemental state? For example, sodium, zinc, this is an element, copper, iron, all right? In their elemental state, they have an oxidation state of 0. Even oxygen, gas, this is 0. They are in the elemental or molecule. Anything on that? Oxidation numbers for monatomic ion is the same as the ionic charge. This is where you use the periodic table. Monoatomic. These are monoatomic ions. Sodium, this is +1. Calcium, this is +2. All right. Oxygen or oxide, -2. Nitrite, this is -3, and so forth. Monoatomic ions. Monoatomic ions. How do we know? How do we know which atoms have an oxidation state of 0? That's a good question, Jennifer. It is, all right, when it is in elemental state, it has an oxidation state of 0. So to answer that question, you got to look at if it is an element or a compound. Let me give you an example here. Sodium, all right, and sodium chloride. If you look at these two examples, I know this is an element, it's by itself, but this is a compound, and I will assign oxidation state based on the, we're going to talk about that, but based on the formula, based on the ionic charge in writing the correct formula for ionic compound. I know this one has a +1, this is -1. So oxidation state here is, this is +1, whereas this one is 0. So by looking at its by itself, it is an element. It's not a compound. Elemental state. On the periodic table, all right? Each box on the periodic table represents an element. That's how I know that it is an oxidation state of 0. Jennifer, are we together? So far, so good? It is. By looking at it, the chemical formula, the equation. If you look at the equation, the element by itself, then oxidation state is 0. And of course, there are some other exceptions you got to look at, such as oxygen gas. If it is naturally occurring, we're going to talk about that. So when it comes to rule number 2 here, monoatomic ions, it's just the uncrossing over in the compound. This is where it comes, this is where the ionic compound comes in and predicting the ionic charges. I gave you an example of sodium chloride here. All right. Monoatomic ions. This is monoatomic ion. This is monoatomic ion. This is monoatomic ion. It's by itself, not polyatomic. The oxidation state for this is +3. This is +2. This is -2, -3. Sorry. So for monoatomic ion, you use the periodic table to predict. If it is forming more than one charge, such as copper 1 and copper 2, the Roman numeral is the oxidation state. You have to understand monoatomic ion. It's just by itself. It's just going to use that. All right. That's rule number 2. Now, there are some exceptions for peroxide, all right, in the group 7. You got to see when you're dealing with the peroxide and non-metal. These are just few exceptions for peroxide. It end up with -1, all right, oxygen. But in peroxide ion, it ends up with -1. What is that means? If I have peroxide such as this, that means for a neutral compound, I don't see any overall charge in peroxide here. So that means each hydrogen is +1 times 2 is 2. Plus, for each oxygen, it is -1 times 2. I end up with -2. -2 and +2 give me an overall charge of 0. I don't see anything here. So for peroxide, oxygen has an oxidation state of -1, but generally oxygen have an oxidation state of -2. Fluorine, of course, group 7, they do have -1 using the periodic table, Now, the sum of oxidation state, all right, in a neutral compound is always 0. Rule number 4, the sum of oxidation number in a neutral compound is always 0. Here is an example of a neutral compound, sodium carbonate. I don't see an overall charge, all right? And if you are asked to find the oxidation state of each element in this compound right here, the summation here being talked about is, and this is what I've seen working for most part, you assign the most electronegative element using the periodic table, the one at the end, take first priority in assigning oxidation state based on the periodic table. And also the first one, take first priority in assigning oxidation state using the periodic table. Using periodic table, all right, sodium is +1, that is it's group 1. Oxygen is -2. Oxygen is -2, but we don't know for the middle element, or in this case, carbon. We do the mass here and we equate to 0, that 2 times 1 for each sodium plus X for carbon plus 3 times -2 for each oxygen equals to 0. We will see when we don't equate to 0. Gonna come back to that. So this is X minus 4 equals to 0. Where am I getting 4? This is -6 plus 2 here give me -4. This implies oxidation state for carbon is equals to +4. So if the question was assign oxidation or find the oxidation state of carbon, I'll equate to 0 and give it to that. If it for all elements, and then sodium will be +1, oxygen is equals to -2, and carbon equals to +4. That's how I've assigned oxidation state using rule number 4. That is how you assign oxidation state. 4, polyatomic ion. For polyatomic ion, such as sulfur, sulfate, for example, sulfate like that, This is sulfate, polyatomic ion. We equate to the overall charge. And remember what I just said. The far or the most electronegative, maybe I haven't talked about electronegative, but the one on the far right, take first priority by assigning the oxidation state, using the periodic table, predicting its ionic charge. If you look at sulfur and oxygen, they are in group 6. And you cannot say, let me assign sulfur oxidation state of -2 because of the, no, the one on this side I've seen working take first priority. By saying, this is question mark, I don't know what it is, but oxygen will take first priority. This one will be -2, all right? So I don't know what the oxidation state for sulfur plus each oxygen is -2. It takes first priority. It's the most electronegative. Time is 4 of them. There are 4 oxygen equals to the overall charge in polyatomic ion. If it was -3, positive, whatever, you equate to that. Okay. So x minus 8 equals -2, which means x equals to 8 minus 2 equals to +6. So sulfur equals to +6, and then oxygen equals to -2. That's how you determine the oxidation state of an element in polyatomic ion. You may wonder why are we doing this? Why can't we just use the periodic table and say, no, there are some other concept taking place behind the scene, which we cannot go in details why. But remember, you cannot memorize. You know, when I took this course, I tried to memorize and say, okay, my instructor will ask me, the oxidation state of sulfur, and I say, I remember oxidation state of sulfur was +6. Let me guess and shade and bubble out +6. No. In some cases, let me tell you, in some cases, oxidation state of sulfur can be +2, can be +4, can be +6. It can be more than one oxidation state. And that's why we have to do the math. You have to do the calculation. Now, Anthony, why is it equals to -2, not 0? Thank you. Because this is a polyatomic ion for a neutral, and that is why rule number 4 here talks about neutral compound. But when we are dealing with polyatomic ion, you equate to the overall charge for polyatomic ion. At this point, you should know that this is polyatomic ion carbonate. This is a polyatomic ion phosphate, all right, with an overall charge of -3. This is a polyatomic ion nitrate, all right, with an overall charge. So I'm dealing with polyatomic ions. There was a table, or there was a chart I posted online on polyatomic ion. You know what polyatomic ions are from chapter 2. So I didn't pick -2. I paste on what is existing in nature, what is still there. All right, so be careful. They might give you a worded question that what is the oxidation state of phosphorus, for example, in this case, and they don't give you the formula for phosphorus. You have to be able to write the formula for those. And I'm gonna show you how to do that. If this phosphorus, for example, not phosphide, I meant to say phosphate. I meant to say phosphate with an overall charge of -3. This is phosphate, ATE, ion. We equate to the overall charge by saying, remember that oxygen, the one on the right side, take first priority. So this will be -2. This will be question mark. It can be anything. You have to do the math and say X for phosphorus plus -2 for each oxygen times 4 equals to -3. -3 because it is an overall charge for polyatomic ion. And x minus 8 equals to -3. X equals to 8 minus 3, and x equals to +5. So in this case, what I'll do is phosphorus is +5, oxygen is -2. I've seen students multiplying it by 4. Say, all right, I had 4 oxygen, let me multiply by 4, and then I end up with -8. No, question will be for each element, for each oxygen, not total number of oxygen. You know, sometimes you may see a multiple choice, and when they make those questions, they think that student will make a mistake of multiplying by 4 and say, I remember my instructor, he was multiplying by 4 or whatever the number is for each element. So Anthony, it's based on the overall charge of polyatomic ion. If it is a neutral compound, you equate to 0. If it is a polyatomic ion, you equate to the overall charge of polyatomic ion, all right? And remember the subscript, how it works. We're gonna use that as a multiple also. Let's see, what is the oxidation number of nitrogen in nitric acid? Somebody try, be honest, you know, let's see if you can get it. Somebody try. Someone try for us before I show you. Do the math, remember the trick. How I use it in this one, sodium sulfate. What did I say? How will you do that? There are 2 elements which take first priority. I know some people can guess and get it, but how do you determine the oxidation state of nitrogen in nitric acid? Do the math. B, somebody B, Dorian. All right, let's do the math. Take steam elements, that is hydrogen and oxygen, take first priority in assigning oxidation state based on periodic table. So in nitric acid, like that, this will be -2. I'm using periodic table. And this will be +1. Cannot be. Yeah. So let's put a question mark right there. I'll say 1 for hydrogen plus X for nitrogen plus 2 times 3, no, -2 times 3 equals to 0. We equate to 0. So X plus -5, this is -6, and this is +1. So this is where I get -5 equals to 0. So X equals to plus 5. All right. When normally I have face-to-face class, I get me my easy pattern. See, that's easy. All right. So correct. Thank you. Thank you, Dorian. Is B correct? So that's how you determine the oxidation state of number as a result of, you know, gaining or loss of electron. I want you to do practice. This is maths. Keep track of where the electrons are going in oxidation reduction reaction. All right. You should be able to determine the oxidation state or oxidation number for an element in a compound. Remember rule number 1. If an element is by itself, you don't use the periodic table, it's 0. So read those the rules again. Be familiar, because there will be a question on oxidation state the next quiz. Now let's see. Somebody had, I think Jennifer had asked whether it is double replacement or single replacement. Yes, there are 2 types of replacement reaction: double replacement and single replacement. single replacement displacement. You displace something, you replace. It's the same thing. Don't get confused. You may see displacement or replacement. It's the same thing. All right. Replacement or displacement is the same thing. It is of this type. All right. A plus PC going to AC plus P. We assume that this is what? This is a cation. This is what? This is an ion, negatively charged. And this is positive. This must be metals or cation that is positively charged. Will a metal replace another metal? We will see momentarily how the single replacement take place. Versus double replacement, so that you don't get confused. This is double replacement. CD. This is cation. This is an ion. This is cation. This is an ion. So this will replace C to combine with that, and this one will combine with that in the product side. So what we'll end up with is AD plus CB. All right, AD plus CB, and that's a double replacement reaction to differentiate the two. Single replacement reaction. In single displacement reaction, all right, in single replacement reaction, you have to look at or understand the activity series chart. It's what we call activity series. I'm gonna come back to this. I don't want just you to memorize this. I'm gonna come back to this. But to understand single replacement reaction, you need to understand the activity series. I'm just gonna blow this one up for you to really see. Okay. Activity series is a list of few selected metals or elements on the periodic table, okay, listed from the most active or to the least active or is to lose the electron. Remember the oxidation is loss of electron. So the one at the top right here loses electron easily compared to this one might not even, gold cannot react, platinum, they are non-reactive, right? They don't lose electrons. So at the top can easily lose its valence electron, and we're gonna talk about that, but just let's say electron. The ease at which it loses, this is ranked. I don't expect you to memorize this. I'll allow you using the exam, all right, the activity series, you will use that, but it is important to understand how it works. How do you read it, okay? And that's why I'm explaining to you. Not this, it's metals, right? But here we have oxygen. That's why it is highlighted as blue. It is not a metal. It's the only element on the activity series which is not a metal. But here are the metals. You got to pay attention. In single replacement reaction, all right, in single replacement reaction, The one above the element will replace something below it, but something below will not replace something above it. So for example, let's see how this one works. Magnesium, if we go back to this example here, why do we say that the reaction will take place to produce hydrogen gas and magnesium chloride? Of course, it's balanced that. It is based on the activity series. This metal, you look at the position on the activity series with respect to hydrogen. If it is above, if the element is above, and then it's going to replace. In this case, hydrogen is below magnesium. So it's going to replace hydrogen. It's going to replace. That's how you read the activity series. I'm going to show you an example where, the reaction will not take place. Okay. So in this example right here, magnesium is above what? Hydrogen. It's more powerful, it's more active. You can say more active. You look at it and it will replace. And then you have to write the correct formula for your, product using the periodic table. That magnesium is in group 2 and chlorine is in group 7 chloride, and magnesium chloride is written this way. I don't want you to write and say, oh, it's going to replace this way. Common mistake student make is just, let me just show you. I'm just writing something here and, I didn't show you what I am trying to say here, that student tried to write the chemical formula. This is wrong. Using the crossover rule, this is the correct formula for magnesium chloride. We're writing your product in single replacement reaction. And remember to assign the oxidation state based on what we just talked. This is magnesium by itself. Oxidation state is +1, right? Balance the equation and you end up with that for single replacement reaction. You're gonna use this table. Even though hydrogen is not a metal, it's one of them. It produces hydrogen gas. Elements above hydrogen will always react with acid to produce what? To produce hydrogen gas. Element below it will not react with an acid. For example, let's see what that means. If we have this Fe, this is solid, plus HCl, will it form up? Will the reaction take place? If you look at iron, all right, iron is above what? Iron is above hydrogen. Therefore, it can either be iron 3 or iron 2. Let's say iron 2 plus hydrogen gas. Remember, it's not going to be hydrogen. Common mistake I see student forgetting that it produces hydrogen gas. All right, yeah, produce hydrogen gas. Violated hydrogen gas. Don't assume it's just going to replace that. It produces hydrogen gas. This is chlorine. So let's balance the equation. We need a 2 in front of that, and the equation is balanced. Hydrogen gas will be produced. If I have, say, copper plus HCl, It does not mean the reaction will take place just the way this one took place. No. Where is hydrogen will? Will hydrogen be replaced? Hydrogen is more active. Hydrogen is above copper. It won't let go away the chlorine in this case, and we say that this is no reaction. No reaction. No reaction. This one is below, so we say that it's not powerful. Yes, Jennifer, you will use that. Yes, I'll allow you to use the activity series chart, but I'm walking you how to read it, how to interpret. What do you expect as a product? So all metals reacting with an acid will produce hydrogen gas. And I was showing you why, or situation where there will be no what? No reaction, no reaction. Let me take a pause here and ask you a question. Any question on reading the activity series? Any question on reading activity series? So know how to read that something above replaces something below it. It's got to be a single replacement reaction. Something below it will not replace something above it. Copper is above what? No, copper is below hydrogen and it will not replace in this case. And if an acid is involved, hydrogen gas will be produced. You know what an acid is. We talked about that earlier on. So reactive metals is oxidized. That means they will be made to lose electrons. You're keeping track of, oxidized. Remember, oxidation is loss of electron. Reactive metal are oxidized to cation. Look at calcium here, oxidized. Oxidized. Magnesium is 0 elemental state. Reactive for magnesium chloride, the oxidation state is positive too. It has lost electron. It has been oxidized. To oxidize is to make it lose electron. Therefore, if you look at the term here, we talked about the oxidized magnesium or active metal being oxidized. It's because it has been made to lose electron. So magnesium. Look at this. Silver nitrate and copper. If we go to activity series, where is the position of silver with respect to copper and vice versa? Will copper replace silver? The way you look at this is, if copper is above silver, and then it will replace. If silver is above copper, then we say, and of course this one, I don't want you to memorize. Let's go back. Here is copper, and silver is below. So that means copper is more active than silver. Copper is more active than what? Than silver. So it's going to replace, it's more powerful. So if we go to this equation, it's going to replace. And what are the product? Copper 2, all right? So long as you balance the equation, I know there is copper 1 and there is copper 2. So long as you balance the equation, that's fine. My battery is about to run out, that's fine. Now, how do I know the product? Because you have to know this, there is silver nitrate. There is silver nitrate here, which will produce what? Silver is +1. Silver is +1, and nitrate is -1. How do I know that it's polyatomic ion? And then when it react with copper 2 now, to replace that, there was nothing with copper. So I'm gonna write my product as copper 2 nitrate. and then you balance the equation. That's why we have 2 here and then 2 here to balance, and then you put, the equation should be balanced. Okay, you will see that. All right, you'll see in the problem that you have. Remember law of mass conservation. That's how you predict your product upon determining that reaction will take place. The next thing is to write the correct formula of your product, and then you balance the equation. Don't just try to memorize and say you will ask me about this equation and I'm gonna know that there is a 2 in front. You have to look at what species are involved. Elements higher on the activity series are more reactive and they will exist in ions. It's the same thing, we do that. Let's see. Does reaction occur when aqueous solution of nickel 2 or nickel chloride is added to the test tube containing zinc? So the question here is, we have zinc in elemental state plus nickel chloride. Will the reaction place? If yes, we have to write the balance the equation. So I need to have what? I need to have the activity series right here. Nickel, where is nickel? Nickel is here. And zinc is above. So zinc is more active than nickel, and the reaction will take place. All right. So here, nickel. All right. Nickel plus zinc, what? Zinc chloride. This is aqueous. And the same, and then you balance the equation. So that's why you use the activity series. I'm looking at the 2, zinc and nickel. If zinc is above nickel on the activity, and then single replacement will take place. And it happened that zinc is above nickel, so it's powerful, it's more reactive, and the reaction will take place, and you write the product, balance the equation, turns out to be that. All right. Any question on activity series? Any question on single replacement reaction? Let's switch gears to 4.5. So this one, the reaction will take place. The reaction is yes. You can just, unless you understand how to read the activity series chart or table, and then you may end up just guessing. You may get it, you may not. So let's shift gears to 4.5, concentration. Concentration is a unit of measurement used by chemists to express the amount of solute particle in a solution. The relative amount of solute in a solution, and in particular, when we say amount, it's the amount of number of moles. Number of moles. It's a convenient unit. Unit of concentration is used to express this. It's the same as molarity. This is unit of express which is determined by, it's just like density equation, number of what? Mole over volume in liters of solution. Maybe I should write it in full. and say what? Volume in liters of solution, not solvent, all right? Not solvent. Students just change the volume of the solvent to liters and they divide and they get it wrong. And M stands for molarity. You may not be given the number of moles, but you may use this equation to find the number of moles by itself first before you plug it in the equation. Number of moles can be obtained by taking the mass of solute in grams over what? Molar over molar mass over molar mass. You may use this equation 3 here to find the top part. That's the number of moles. So concentration, just used to express the quantity of solute in a solution. Solute is what you dissolve. And when we say quantity amount, it's not in grams, it's in the number of moles. You use the number of moles, we call this concentration. We interchangeably use molarity and concentration. What's the concentration of this solution, or what is the molarity? It's the same thing. It's a measure of the number of moles of solute, what is being dissolved, and the volume of solution in liters, not volume of solvent in liters. Remember how we define solution. A solute is present in less amount. And using that equation, you can either regenerate other two equations. You can relate molarity with molarity times volume in liters, all right? Or volume in liters could be given by number of moles of molarity. Just to show you some of the equation you have to, or you should be able to derive, all right? You should be able to derive from this equation. So I may give you in the exam this equation, and I'll ask you to find the number of moles. So change the volume to what? To liters. Let's see an example here. Calculate the molarity of a solution containing 0.175 0.175 moles of zinc chloride in exactly 150 ml. Using this equation, number of moles, all right, over volume in liters, you have to change the volume to liters. No one will tell you change the volume to liters. You're expected to know that. This is number of moles over 0.150 liters. Let me get my calculator from my calculator real quick. So 0.175 divided by what? Divided by 0.150, and I have 1.17. This is moles per liter. It's the same. That's the unit for molarity. Or sometimes you'll see this 1.7, 1.17 with an uppercase M. Uppercase M stands for molarity. Molarity or 1.17 moles per liter. Moles per liter. It's the same thing. We use that. That's how you determine the molarity given the number of moles. Okay. How many milliliters of 6.0 solution are needed to provide? This is, we haven't talked about this, but we'll come back to this. I'm gonna come back to this equation. All right, I'm gonna come back to this equation. So that is what you need to know as far as molarity is concerned. Changing the volume to liters, finding the number of moles. You may not be given this number of moles, but you have to use this equation. Number of moles is given by the mass in grams of a molar mass. Use the periodic table. If you are not given the molar mass, you know how to find the formula weight, you know how to find the molecular weight, and then you divide to get the number of moles, and then you get in there. I'm gonna come back to learning check number B, all right? And first, let me walk you through how to prepare a solution, because you will prepare a solution at some point. That means you will weigh out certain grams of solute to dissolve in a given volume of solvent to end up with a certain or the desired molarity of solution. Always you weigh out first your sample, and this is the sample, and say this is 100.0 ml mark. You will weigh out the sample and transfer quantitatively into your flask. Not to fill the flask to 100 ml mark and then you add your solid. No, it's not gonna work. You'll end up with more matter in your solution. Remember, matter cannot be created or what? Or destroyed. You start with the solute first and dissolve with enough what? Enough solvent until it is dissolved completely before you top it up to the mark. You may use the dropper pipette. You may recall that in the, you do that. That's how you prepare a solution. You weigh the solvent and the solute, put it in a flask, dissolve it, and then you adjust the volume to what? To the desired flask. So if you look at what is happening here, you weigh fast, transfer it onto the flask, you add the water, enough to dissolve before you adjust the volume to the calibration mark. There is a calibration mark, and you know how to read the meniscus. Remember this, please. I know you're gonna make that. I don't want you to fill the flask with water first, and you try to do what? You try to dissolve. It's just like, when you make your coffee, go to Starbucks, and then they fill the what? They fill the coffee all the way. You don't have room for what? For sugar. If you put sugar in there, it's gonna overflow. Matter cannot be created or destroyed. That's what's going on. That's simply how to prepare the solution. Read on how to prepare, and you will not go wrong. I know you're gonna do that. Sometimes in the lab, all right, some reagents are procured with high concentration and you have to bring it down. Even in our homes, when you go, those concentrated drink where they say, oh, you got to empty everything into the pitcher and then add this, you're diluting. Dilution is bringing down a more concentrated solution to what? To a less diluted. We call it dilution. There is what we call dilution law. This is another way of determining the molarity. Remember dilution law. M1 V1 equals to M2 V2. That is, a more concentrated solution is taken down to what? To a less concentrated. Sometimes this equation is MC for concentrated, V for concentrated equals to what? M dilute and V dilute. These two equations are dilution equation or dilution law. It is bringing down a concentrated solution to what? A less concentrated or the dilute solution. Remember, we have what? One, two, three, four. We have four identities in the dilution law. You will be given three, and you are asked to find the fourth missing identity. I have four identities. The question can be what? Can come from anywhere. If you are looking for, say for example, a question mark is right here, and then that VC will be given by M dilute and V dilute over M concentrated. I'm just rearranging this equation, making VC the subject of the formula. I divide both sides. You know how to rearrange that. Out of this, you should be able to generate four equations. I'm not going to give you all the four equations. You should be able to do that. So in the exam, I'm just going to give you my equation. This one right here, what you see here, you ask is to generate, all right, an equation you need to use in order to answer the question, all right, in order to answer the question. This is called dilution law. Remember, MCVC, subscript C for concentrated, subscript D for dilute. It can be M1, V1, M2, V2. Maybe the text is using D, but the lab manual will use 1 and 2. Do I need to change the volume to liters? No, but it should be uniform. It should be liters, liters. It should be milliliters, milliliters. It doesn't have to be in liters, all right? Okay, let me, work example here before I go to B in the previous slide. Let's read this. How do you assign V1, M1, V2, M2? Is by reading the question, and the first thing you assign is your initial conditions. If I look at this problem, how many milliliters of solution of stock solution? How many milliliters of stock solution of 6.0 molarity concentration nitric acid will you have to use to prepare 110 ml of 0.5 molar nitric acid? This is M1 V1 equals to M2 V2. It's easy. M1 is 6.0. V1 is what I'm looking for. I'm taking to what? I'm taking to 0.00, 0.500, and this is 110 ml, which means V1 equals to M2 V2 over M1, which is 110 ml, and use the units times 0.5000 m over 6.0 m. Molarity goes away, we remain with liters. So I'm just gonna divide that. It is what? 110 times 0.5 divided by 6. It is 110 times 0.50 divided by 6. I end up with around 9.2. 9.2 9.17. All right, let me just 9.2 ml. Going with significant figures. So that's how I find what the volume. The key thing is knowing that this is a dilution problem by looking at what you are given. By looking at what you are given, the problem. Let's see the problem I had before. Here, I'd say I'll come back. I knew the reason why. Okay. If you look at problem B here, how many milliliters of 6.00 molar NaOH solution are needed to provide 0.350 molar? You see three significant figures. This is a dilution problem. M1 V1 equals to M2 V2. And how many? That means I'm looking for V1. M1 is 6.00 molarity. And M2 is what? 0.350 M for molarity. And how many to provide moles? Oh, okay. This is not an dilution. It's not gonna work. If you look at this, we have two question marks. It didn't even ask. I was trying. I made a mistake. That's how you should learn. Okay, we learn how through mistake. I learned my mistake. So it's not gonna work. This is not a dilution law, but we are going to use this. Molarity equals to number of moles over volume in liters. We have the molarity, we have this, and we have that. So volume in liters is given by number of moles over molarity. I rearrange the equation. You know how you take that and then you bring that. That's how I end up with that. So number of moles is 0.350 over what? Over 6. And remember the units will be what? The units will be in liters. The units will be in liters. So 0.350 divided by 6. This will give me 0.0583, and this is liter. So if I divide multiply 1,000, this is 58.3 ml. Remember, 1 liter equals to 1,000 what? 1,000 ml. You're expected to know that. That's what you need to use in B. Sorry about that. I thought it was dilution, but it's not gonna work. It was just a molarity equation. I want to stop here today, and we will pick up from section 4.6. I think it's section 4.6, that is the solution stoichiometry, and move on to chapter 5 on Tuesday. The class is dismissed. I want to take a moment. If there is any question, you may ask at this time. Other than that, thank you for tuning in today. Continue working on the exam. It's gonna be over tonight. I saw it's raining. Be safe out there. Continue sanitizing. I'll see you next Tuesday. Thank you. Have a good day.